Thank you. Good morning. I'm going to share about a project that's been a collaboration between a few of us that are in the Pacific Northwest at the Pacific Northwest Research Station in Oregon, a few people who are with Oregon State University, and a few people who are in the Southwest with the Forest Service. And we are endeavoring to create an STSM that is climate informed, and we want to model Arizona and New Mexico. So there's two models involved in this work, MC2, which is a dynamic global vegetation model, and an STSM that was developed previously for modeling the Southwest. So it was already in existence, and we wanted to take the strengths of these two different models and work them together. So our DGVM, it outputs spatially, it simulates carbon cycling with climate input. It is a deterministic model. One of its shortcomings are that the plant functional type output that it produces is pretty coarse grained. We don't have a lot of detail from MC2. The STSM, on the other hand, does output spatially or non-spatially. It's very good at successional change, but it did not include climate impacts. And it's, of course, stochastic, and it has a very high granularity for vegetation. So we wanted to take what's good about these two things and draw them together to create an STSM that is climate informed based on climate influenced vegetation change in MC2. There is a bit of history to this work. So over the past 10 years, there have been people who've already tried to do this. Mainly what they were working with subregions in the Pacific Northwest, so smaller areas. The largest area they tried to model was Western Washington. That's what's up on the screen. This is from one of the papers that came from that work. But in almost all of those cases, the areas they were modeling were forested and they were fairly homogeneous as far as vegetation goes. On the other hand, we're taking on a bit of a challenge by trying to model Arizona and New Mexico. This is a map of ecological response units, or ERUs. That is the ecosystem mapping method of the Southwest the people in the Forest Service are using. So examples would be ponderosa pine forest, mixed conifer dry forest, semi-desert grassland. Those would be ERUs. So there are more than 65 different ERUs represented in this map. So a lot of diversity compared to areas that were modeled previously. But it's also a diverse region in terms of physical characteristics like elevation and climate zone. So while we are taking on the whole Southwest, we have a test case scenario, and that is the Lincoln National Forest that is in New Mexico. The rectangular area there is showing sort of the whole area that we modeled for our test case. So we have the Lincoln National Forest and some of the outlying areas. The map on the left is our ERU map. So lots of detail there, high resolution, really good granularity for vegetation. On the right is out from MC2. So for that same area, MC2 only resolves about 10 different plant functional types. So we do have a difference in resolution, in granularity for vegetation, and that does create a bit of difficulty in what we're trying to do. The way we're doing this is very straightforward. Conceptually, although when we work it out, it gets a bit complicated. But what we do is we start with our ERU map, so known vegetation on the ground, and then we run MC2 just for the historical, not quite up to present day, but for recent historical period. We run it with PRISM data, so known climate data, and we look at vegetation output for the recent historical period. And then we just take those two maps and sandwich them together, do a spatial overlay, and ask, okay, what ERUs are overlapping with what plant functional types from MC2? So it's a really straightforward idea. But we do, especially because of the difference in resolution, we do get a lot of noise, and so we have to do some extra work to figure out, okay, what types are actually associated with what. So we end up with a massive pivot table from which we get a crosswalk for ERUs to plant functional types. That's just a small sampling of it on the screen there. So then what we do is we run MC2. In this case, we ran it up to the year 2100. We ran it for 10 different GCMs under the RCP 8.5 scenario. Ideally, what we would do is we would take output from every year of MC2 output and we would crosswalk each year to ERUs, but that would be a tremendous amount of work. So since no one quite has that time, we just took mid-century output and late-century output from MC2. And using our crosswalk, we generated that output back to we took that generated output, crosswalked it back to ERU. So then we have 3 ERU maps. One that's known, historical, one that is mid-century projection, and one that's a late-century projection. So then we can take those 3 maps and we create a set of transition probabilities for ecological response units. And then that set of transition probabilities goes into our STSM model, and that's how we get climate change impacts into our model, is through vegetation change as derived from MC2. One other thing that we did in this work that was not done previously is we did look at climate zone. We did one set of transition probabilities for all of the Southwest, but we felt like that was not capturing the diversity of transition. I mean, it's a large area, and we felt that it wasn't, one set was just not working for that whole area. So we started to look at climate zone. And again, it's playing the game of how much do we need to do to make an accurate model without having to get into great computational expense. So we created two sets of transition probabilities, one for this area that's being outlined in red. We're calling that the temperate zone. We have one set of transition probabilities for the temperate zone. And then we created a second set of probabilities for that orange area, the more southerly area. So now we have 2 sets of transition probabilities. And the rectangle on the screen is showing our test case area, the Lincoln National Forest, where we do have both climate zones represented. Okay, so what I'm showing here is a diagram that represents transitions as derived from our model. So the diagram has links and nodes. The nodes are the ERUs. The links between the ERUs are transition probabilities that we derive from this process. I'm just highlighting mixed conifer dry forest. I mean, the actual transition diagram is much more complicated. This is just highlighting what's going on with mixed conifer dry. There's commercial interest in that ERU. I understand that it's difficult to manage, so there's interest in that particular vegetation type. So what we're seeing here is, this is just for one GCM driver, CAN-ESM2, and we're looking at transitions up to mid-century and then transitions to late century. So what you can see is that on the left, the mid-century transitions, we see mixed conifer dry. It's transitioning somewhat to pinyon juniper woodland, ponderosa pine forest, and juniper grass. The late century transitions are showing that actually now we have some other types that are feeding into mixed conifer dry. So we do see a change in dynamics from over the course of those 100 years of simulation. I wanted to give a sampling of our output, what we can do with our model. This is showing how the quantities of 7 different ERUs are changing over time. So we did, once we got our transition probabilities into our STSM, we ran that for 100 iterations. You can see that, this is only for 2 different GCM drivers. If I put all 10 up there, it gets really messy fast. So this is just showing, contrasting what we see with 2 different GCMs driving the model. For some ERUs, projections are very similar. For others, you do see a difference in what they're projected to do. A mixed conifer dry forest has got the red boundary around it, just highlighting that one as one where we do see a significant difference in what's projected to happen to that ERU. If I look at just mixed conifer dry and I look at all 10 GCM drivers, I see that there is a wide range of output, a wide range of projections for that particular ERU. I mean, some of the models are actually saying, oh, it's going to decrease. Others are saying it's going to increase, some by a lot. So this is where we have to say for this ERU, we have to start thinking about adaptive approaches to management, because there are so many different pathways that ERU could take. So just one management plan for the future is probably not cut it for managing that ecosystem. One last thing, and maybe the most important thing that we can look at from this work is desired class. So in the model, mixed conifer dry forest does have several different successional states that are included. Planners working in the Southwest have a desired state that they would like to see mixed conifer dry in. And the desired state is an uneven aged forest with medium large trees and less than 30% cover. So again, this is just for 2 GCM drivers, but you can see that for both of them are saying that the proportion of mixed conifer dry in that desired class is at best maybe a little over 20%. So not what managers would like to see. On the other hand, if we look at, well, what's the state that is hanging out in? Well, most of it's hanging out in this early development state where there's seedlings and saplings and less than 10% cover. So this is where we can talk to managers and say, okay, you might want to find some ways that based on our model output that can get more of mixed conifer dry into that desired class over the course of the future. So I have to mention something about assumptions and uncertainties in our model. We did assume the ERU to ERU transitions are only happening with climate change. So we did not model ERU transitions between ERUs from any other driver, just climate change. We only have one set of thresholds in MC2 for temperature and precipitation that determine carbon and vegetation. That's probably a little too coarse for all of Arizona and New Mexico. We, of course, have inherent uncertainty in our model structure, but we did, in a way, kind of build uncertainty into our model through the spatial overlay. So where we have small sample sizes for ERUs, there's a greater uncertainty. So we already know right there that there's a variation uncertainty from that process. And just to highlight a few summary points. So this approach can work for a larger area. Like the Southwest, but we can also focus in on subregions like the Lincoln National Forest. We are looking at this output as what might be the most likely outcomes, right? So it's a probabilistic model. This is showing what might happen. What we can do at this point is start to add in management approaches like prescribed fire to see if we can push some of those state classes into more into the desired states for different ERUs. And to quote one of my collaborators, the reason we're doing this was to take the big picture into the little picture. So we can have a really nice map of ERUs across the whole Southwest, but what we want to do is drill down into these specific desired classes of these ERUs and ask, well, what is projected to happen? And as I already kind of mentioned, the results are saying for at least some of them, it's going to be an adaptive approach that we'd have to go with. So just a nod to my collaborators and funders, and with that, I can take any questions.